Welcome and hello. This is a video exercise in HEC RAS, and in this exercise we are going to be dealing with navigation dams. Navigation dams is a boundary condition that's available for inline structures, and it allows the model to regulate the water surface elevation either at the inline structure or further upstream. All right, what I have on the screen here is my HEC RAS. I'm going to go ahead and start from the beginning. So let's go New, Project, and then navigate to the directory we want to save that project in. Okay, I'm going to give it a title. I'll just call it exercise 17 and then click OK. And then for the unit system, just go ahead and click OK. All right, down below here, we have the geometric data window open. So we're going to go ahead and create the geometry file first. Go edit geometric data if you don't already have that window open. And then I'm going to start by sketching out a river reach. So just a single left click to start, and then add left clicks as you want to add vertices to that reach. All right, so I'm going to go ahead and call it river A and reach 1. And we're only going to have one river and one reach here, so that's that. Click on cross section. And then what I want to do is options, add a new cross section, river station 0, and OK. Next, I'm going to start typing in station and elevation data. And I have that all typed in right there. And then distance downstream will be 0 because this cross section I'm editing right now is at river station 0. There's nothing downstream. Okay, after that, we got Manning's N. So I'm just going to type in some typical values here. And then the left overbank station is going to be 30, and then right overbank will be 60. I'm just looking at the geometry right here. All right, click apply, and here is a image of the cross section over here, a little sample view. Next, I want to add a cross section at the very top of the reach, and then going to interpolate a few intermediate cross sections based on the geometry of the two I defined manually. So I'm going to go up to options now, and then copy current cross section. I'm going to call this 10,000 river station, so almost 2 miles upstream. And I need to do a couple more things here. I need to add the distance downstream, which is 10,000. Okay. And I also want to increase the elevation because I want the water to flow downstream. So options, adjust elevation, and then I'm just going to add 20 feet. So that would be a 0.2% slope, and click apply data and then close. All right, now I want to go ahead and add some intermediate cross sections here. So I'll go up to tools, XS interpolation within a reach. And then, yeah, it'll be for the entire reach. So I'll just type in the distance. I'll say it's 1,000, interpolate, and close. Now I have my interpolated intermediate cross sections every 1,000 feet. I'm going to go ahead and save this geometry file by going File, Save Geometry Data. I'm just going to call this Base, and then click OK. All right, so what I want to do next is add an inline structure. So to do that, I'll click on the Inline Structure tool right here. And let's see, I'm going to put this inline structure at river station 1900, which is right here, sort of towards the downstream end of the reach. I'm going to go start with options, add an inline structure. And then, like I said, it's going to be 1900. I'll click OK. Here's the cross section at river station 1900. And then here's the river station at river 2000. So it opened up the ineffective flow area for some reason. Cancel that. Now, what I'm interested in here is the elevation of this overbank, not the invert so far. So let's see. The invert's at 204. The overbank appears to be at 209. Okay, so that's fine. I'm going to go ahead and remember that when I define the inline structure geometry. So I'm going to click on Weir/embankment. This is back in the inline structure editor. And then I'll move this over here for now. What I want to do is distance downstream from the next river station, upstream river station will be 100 feet. The width of the inline structure doesn't have to be particularly wide. Let's just say it's 8 feet. And then the stationing and elevation data is what we need to do next. So I'll just say the stationing is the entire width from 0 to 90. And then again, 209 is that elevation. So we'll type in 0, 209, 90, and 209. Okay, so it's kind of hiding behind the embankment here. The stationing really doesn't have to extend all the way to 0 or 90. It could actually just be from 30 to 60, but anyway, it should be fine. I'll go ahead and add a side slope of 2 to 1 and click OK. So now I see in the preview this embankment that I've added. And what I'm going to do is add a gate. So the gate is what the navigation dam is going to be controlling up and down. to let the appropriate amount of water through in order to, as best it can, maintain a certain target water surface elevation just behind the inline structure here. All right, so I'm going to click on gate, and then let's add a discharge coefficient. This will be a sluice gate. I'll just accept the default gate type. I'm going to move this over to this side here. I'm going to work backwards. I'm going to say the invert first. I'm going to define that as 204.5. I believe the invert of the channel is 204, so we do have 6 inches of dead space, might call it. I'm going to say the height of the gate is 3 feet, and then the width is 8 feet. Let's see what that looks like on the display here once I get it in, and we can make edits if necessary. I'm going to say there's only one gate, so I'll just call it G1. That'll be at station 45 because we have 40 to 50. So if I want it centered, it'll just be at 45, and then I'll click OK. All right, so what we have here is the gate, and that looks pretty well centered and sized, in my opinion. Only really room for one gate of this size in this particular embankment, though. So we're just going to go with that. All right, so let me go ahead and close that. I'm going to file, save the geometry data. Again, it's already saved as base. That's the title. Next, I want to go ahead and edit some flow data. So I'm going to go up to edit and then unsteady flow data. What I have here are the boundary conditions for a few different river stations. We have the downstream river station. I'll click on normal depth, and then I'll go 0.002. That's the channel slope. And then for the inline structure, this is navigation dams. That's what we're going to be doing in just a bit. Before we do that, though, let me go ahead and define the flow rate, the flow hydrograph at the upstream end of the reach. All right, so what I'm going to do here is select the radio button for enter table, and I'm going to use the use simulation time, which means it'll start at the time the simulation starts, so I don't have to actually type in a date or time using this option, but I would if I typed in fixed start time. So I'll just keep it easy, keep it simple, use the simulation time. And then the time interval is set to 1 hour by default, and that's what I want to use, which means that each value here represents the flow rate at the next hour. Right, so it gives me 100 different rows by default, but I can change that if I have more than 100 hours of data by just going number of ordinates, changing that number. But I only have 3 days worth of data, which is 72 hours. So I'm going to highlight those fields, click Control V, because I have those pasted onto my clipboard, and it looks like they pasted just fine. I'm going to click this plot data so you guys can see what that hydrograph looks like. It starts down at 20 CFS, nope, 10 CFS, and then it goes up to 150 CFS. And then it oscillates a number of times during that 3-day simulation. All right, so I'm going to close that up, click OK. And then before I forget, I'm going to go File, save this unsteady flow data. I'm going to call the file 10-150-10, and that's going to help me remember that that's the range of the flow rate and that it oscillates. Click OK. All right, we still need to define the boundary condition here, and this is for the inline structure. So our options here are gate openings, elevation control gate, navigation dams, and rules. Navigation dams is what I'm going to use, but for this first trial, what I want to do, sort of as a comparison, is to just set the gate completely open for the entire duration of the simulation, run the simulation, and then use the navigation dams boundary condition for a separate flow file, a separate plan, and a separate set of results so that we can compare just how well the navigation dam boundary condition works. Make sense? All right, so like I said, this will just be the base case for the flow. And for the boundary condition, I'll go ahead and select this row from the table, click on TS gate openings. And this always gets me. The gate time interval is 1 second, but I'm going to change it to something more realistic like a minute. I'll just set it to an hour. I'm going to set it constant for the entire simulation anyway. All right, as before, we have the option for DSS or enter table, and I'm going to use the simulation time once again. So all I have to do is type in the gate opening. The gate is 3 feet high, so I'm just going to enter the number 3 or 33 a bunch of times here, and I can actually copy that. So 70 to 36. I'm just going to go ahead and copy this so I don't have to type it in as many times. Okay, so I'm going to highlight that, copy, and then highlight the rest, and then paste. All I need is 72 hours. I'm down to 77. That should be fine. Okay, so I'll click OK, and then let me go File, Save Unsteady Flow Data. All right, I'm ready to create the plan, run the simulation, and take a look at the results with the gate fully open for the entire 3-day simulation. So I'm going to go to Run, Unsteady Flow Analysis. I need to go ahead and name this plan using the base geometry file and our 10-150-10 flow file. Again, this refers to the gate fully open. We got to remember that. Save plan. I'm going to call it 10-150-10 just as before, and then copy that to my clipboard, paste it for the short ID, and then run these different processes. Now, also, I need to specify the simulation time. So I'm just going to say January 2020, the first day of the year, and then that's going to start at midnight until midnight 3 days later. Okay. And then, yeah, so 1 minute and 1 hour, that's fine for this data. And then I'm going to go File and save the plan. All right, compute. Let's see what happens. Okay, that looks successful. Didn't see any error messages pop by. Let's go ahead and take a look at the results. I'm going to go up to View, and then let's take a look at the cross section. And then I'm going to go down to the inline structure we have here at River Station 1900. And then Options, Animate. So now it's going to play through an animation of the simulation that it just ran. So I'm going to click the play button here, and we can see the water surface goes up and down. The gate is fully open. Okay, so that's kind of what I expected to see. That looks good. I'm going to zoom in real quick and then just pan over so that I can see the elevation really well. Elevation, we can see that it tops out at about 207.5, maybe a little bit higher. And then the low water surface elevation at 10 CFS. Oops, let me go back. It's like right about here, say 205. What I'm doing is I'm trying to get an idea of what water surface elevation should be my target. So maybe we should aim for 207. That's a nice round number. And then if 207 is our target, like right about here, what that means is the gate is going to close at least part of the way when the water surface or the flow is at its low point to maintain a high water surface elevation behind the partially closed gate. But then when the flow rate is at its highest, like 150 CFS, then the gate will be fully open. At least those are the results I'm expecting to see. All I'm doing here is confirming that I want to set the target water surface elevation just upstream of the inline structure to be 207. And I should probably also keep in mind that 209 is the top of the inline structure. So let's close that. I'm going to go back to Edit, Unsteady Flow Data. And what I'm going to do first is just save a copy of this flow file, but I'm going to save it as a new version with the navigation dam, which will be my boundary condition. So File, Save Unsteady Flow Data as. And what I'm going to do here is just add a suffix of NAV for navigation dam, and then click OK. All right, I don't have to change anything except this boundary condition for the inline structure. So I'm going to click on Navigation Dams. This warning message is telling me that the information of the previous boundary condition will be removed, and that's fine. And now we have the interface here for defining the boundary condition data for that inline structure related to navigation dams. The first one here is how often the gate can change. So if the gate can only change every 3 hours, I would just type 3 hours. That's really not good enough, especially because the oscillations of my flow data is much faster than that. I'm going to go ahead and say 0.25, representing every 15 minutes the gate is allowed to change. And then the initial gate change time, I'm just going to say is 0 hours. So every 15 minutes starting at the very beginning of the simulation. Next up is gate minimum opening. I'm going to say 0, and then gate maximum opening, I'm going to say is the maximum of the gate geometry that's 3 feet high. The user's manual does mention that the first gate group of the inline structure has a minimum of 0.1, so I believe that's kind of overwritten. But anyway, I'm going to set that to 0. And then the gate opening rate in feet per minute, I'll just say it's 1 foot per minute. That's good. That way, if it's completely closed, it'll take 3 minutes to completely open, or if it's completely open, it'll take 3 minutes to completely close. I don't think that's really going to happen or be a big deal, though. All right, down below here, we have the operations to select, either pool only control operations or some sort of hinge point. Since I'm interested in the water surface elevation just upstream of the inline structure, that's what this first option is for, pool only control operations. But if I was interested in maintaining the water surface elevation at a location further upstream from the inline structure, that's when I would use one of these hinge point options. Okay, so pool only. Now I need to set the flow monitor data and the pool control. So flow monitor right here, it's going to be the upstream location that is being monitored for incoming flow. I can use 1, 2, or 3, but I'm just going to go with 1 for now. And I also want to approximate how far upstream to select of a river station because the inline structure is just right near 2000. So let me go back to my results real quick. I'm going to go to view and then profile summary table. And I want to get a sense of what is the velocity of the water. So let me go ahead and turn on the different profiles. Okay, so I'll select all profiles, toggle off max, click OK. Now let me go down to the river station that's close to, actually, you know what? I could just go click on the inline structure. That's better. I don't have the velocity here though. You know what? It's fine. Let me just go back to River Station 2000 because that's just upstream of the inline structure, and I feel that that is representative enough. Okay, so here is the top. Here's the flow rate. It ranges from 10 up to about 150. I do not have a warm-up period, but it doesn't seem to be a problem. If it is, I can add that. All right, so anyway, we're looking at velocity here. It looks like 0.7, 0.8 is the minimum velocity. And then the maximum velocity is going to be at the highest flows, of course. That's right about here. That's 2.36. Okay, so I would say that the average velocity is about 1.7 feet per second. Okay, so if I had 1.7 feet per second times 60 seconds per minute times 15 minutes per gate change, that's 1,530 feet. So the reason I did that is 1,530 feet upstream from River Station 1900 would put me at about 34. So we'll just put it at 3,000. I could use 3,000 or 4,000. Let me go view. I sometimes have to modify this view. This is not geo-referenced. That's why the numbers don't look correct from here, but I just want to change this to allow myself to zoom in on the geometry data. Okay, so I'm going to click OK. And now I want to zoom in here. Okay, that looks good. Here's the inline structure at 1900, and then here is the cross section at 2000, 3000, and 4000. I said 3400. So if I had a cross section at 3500 or 3400, that would probably be the best location for a monitoring station. In fact, I could add additional cross sections here if I really wanted to. But I'm going to select 3000 for my monitoring location. So we can go ahead and close that back to the navigation. And then what I say, 3000. So that looks good. The other tab over is pool control. And where I like to start editing this is the target location. This is the water surface elevation. And remember, our target is the pool, which it means just upstream of the inline structure. We said that our target was going to be 207 feet. And then target low, let me go ahead and just call that 206.8 and then 206.5. I'm just making these numbers up. I'll say 205.5. Okay. And then on the upper end, I'll just kind of mirror the same different distances that I did for below. So 207.2. All right. And then we know the maximum flow is 150. I'll just type 150, but I think any number larger than 150 is appropriate there. And then 10 on the low end. And then for the flow factors above, I'll say 1.05 and 1.1. And then below, I'll say 95% and 90%. All right, so I'll click OK. I have to go ahead and save that data. So File, Save Unsteady Flow Data. And let's go ahead and run the simulation and see how well that navigation dam logic works and what the gates are doing and how well that gate logic can maintain the water surface elevation at 207 just upstream of the inline structure. All right, so close and then run unsteady flow analysis. Here we have our same base geometry file, but now we're using the navigation dam boundary condition for our flow file, but the hydrograph is still the same. So File, Save the plan. I'm going to save this just NAV, same name as the flow file, and then OK. Same thing for the short ID, OK. So I think that is saved and ready to go. We don't need to make any changes to the simulation time window or to the computation settings. So I'm going to go ahead and click Compute. Okay, so that ran. I'll click Close now. What I'm interested in is some of the results. Let's take a look at the cross section first. Okay, so I can already tell that it is working to a certain extent. This is the range of water surface elevations, but let's go ahead and animate it. So options, animate. And before we do, I'm going to zoom in a little bit more this time and then click the play button. There's the water surface elevation. You can see the gate is closing and opening. And the water surface elevation is much closer to our target of 207. It looks like it's going down to a little below 207 and then back up to where it is now, which appears to be the top of about 207.5, 0.6. Let's go ahead and take a look at some other data now. We didn't look at this before, but I want to check out the stage and flow hydrographs. So what we have here is, well, it's River Station 10,000. Oh, oops, I need to change the type. I don't want river stations or cross sections here. What I want is inline structures. Okay, that looks good. Let me toggle off the flow data. I don't want that. And I'm not actually interested in the tailwater elevation either, because that's not what the navigation dam is controlling. It's just this data up here. And it appears to be hovering pretty close to 207. Let me go ahead and right click and then full plot. That's going to recalibrate the axes. So now we have 206.6 is the minimum, and then it goes up to 207.6. At least that's what the axes are up to. So that's approximately the max and min values here. So if you drew a target line at 207 right across here where the mouse is kind of crossing over, that is the target. And it's kind of hard to tell how good that is without comparing it with the original simulation run that we did when we just left the gate fully open. So let's go ahead and do that. I'm going to go up to options and then plans. Now I'm going to toggle on this first plan that we ran, where we just left the gate open, 3 feet wide, high for the entire simulation, and then click OK. Okay, I need to resize the window here real quick. And then I also want to turn off actually, I think I can do that up here. So plot flow. Okay, that got rid of some of them. That's good. And I also want to remove the tailwater stage right here and here. All right, so right click, full plot. Let me go ahead and change the symbology as well. So right click, lines and symbols. So yeah, I want headwater, WS1, blue, no symbol, but I want to make it thicker. So I'll just say 6. How about 5? Okay. And then the other headwater right here, I'll say no symbol. I'm going to change the color to red, and then I'll make, oops, okay. And then I'll use the same thickness, which is 5, and click OK. Okay, this is much easier for me to read. So red is the original, the first simulation we ran where the gate was open, 3 feet wide or high, and the water oscillates between a water surface elevation of 205 up to 207.5. And then blue is with the navigation dam. It looks like the peak is still about the same, 207.5, but the minimum value, the minimum water surface elevation doesn't go down to 205. It's maintained above 206.6. So that's fairly satisfying to know that the gate works that well. There's probably different ways to make the gate work even better, like having multiple gates, multiple gate groups, obviously smaller gates as well, and also more precise time controls. But before we finish up this exercise, I still wanted to look at one thing, and that is how are the gates actually opened and how are they operated? For instance, I believe they're fully open at certain times, but I believe they're mostly closed at other times. So to do that, I'm going to go to View, Profile Summary Table. We've already been here once before. I'm going to click on the inline structure. I'm really not interested in the first plan here with just keeping the gate open the whole time. So I'm going to turn that off. I'm going to go Options, Plans, and then uncheck that plan. Click OK. Now I want to show all the different profiles. So I'll go Options, Profiles, select all, and I like to unselect max. So I'm just seeing like the actual starting at time 0. Click OK. So what I have is energy grade line, water surface elevation, and total flow. And then there's a breakdown between weir flow and gate flow, but it should all be gate flow. What I'm not seeing here is the gate opening. So what I'm going to do is remove these columns over here. They're not interesting to me. And then add the gate opening so we can see how that gate is controlled. I'm going to go up to Options, Define Table. And then here is the fields up at the top. Here are the columns. Let's see. So I want to keep Q gates. That's this one here. And then column 6 and over, I'll just delete, 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 delete. And then I want to search for gate. So GATE. And then here we go. Height of the gate opening. So gate height opening. I'll double click that and then click OK. So now I have this new column here, and this is exactly what I was expecting to see. So it starts at zero point 0.2 feet open, and then it goes all the way to 3 feet, which is fully open. Once the flow gets up to 122, 147, 139, 122 again. And then once the flow rate dips down to 97, the gate closes down to 1.86 feet. And then it looks like 1.4 feet and then less than a foot for the next few hours until the flow rate ramps up again. So this is really satisfying to see like how the flow rate and the gate height opening are operated. Of course, like I said, there's a lot of different options. We could have added different monitoring locations. We could also have used that hinge point operations if we were curious about some other locations upstream of the inline structure and trying to maintain their water surface elevation at a certain value. All right, well, that was it for this exercise on inline structures, specifically using the navigation dams boundary condition.